Hey there. I want to start our investigation in this next unit by just showing you maybe some visuals. So this unit we're going to be investigating polynomial functions. We're going to be investigating polynomial functions. So you're familiar with like linear functions. That's technically a polynomial, a straight line, and quadratics, which you had dealt with in grade 11 math. But we're going to take a look at third degree, fourth degree, and fifth degree polynomials. Okay. So what we're going to do in this unit is we're going to investigate some characteristics, and right now that's what we're going to do, is we're going to investigate some characteristics. So what I mean by characteristics is like x-intercepts, y-intercepts, domain, range, this idea of what's called end behavior. There's another one called multiplicity, which we'll talk about in a little bit. In a further lesson, yeah. So I want to dive in. Maybe just start off with something you already know. Actually, sorry, I'm getting ahead of myself. After we look at the characteristics of graphs, what we're going to do is you've already in the past looked at quadratic functions and factored those. You've developed some strategies on how to factor that, how to just solve roots with quadratic equations. Be it like, you're using decomposition, or you're using the quadratic formula, or completing the square, all those methods you used when you were looking at quadratics. In this particular section, we will need those skills, but we're also going to learn new skills to learn how to factor cubic, so third degree polynomials, fourth degree, fifth degree. So we're going to just elevate from what you've learned in the past. So, yeah, and I think from there, after we kind of learn some skills on how to factor, we're going to look at some graphs, look at equations, and how those two can relate and speak to each other, and how we can apply what we know about polynomials, particularly with the graphs and equations, to answer some problems in the later sections. But we'll ease into it. We're going to look at some characteristics of these polynomials to start. So I want to take a look here. Let's start with the basic quadratic equation that you're familiar with here. So this is a parabola. This is a even degree polynomial, we call that, because the degree of this thing is 2, and the degree is always the highest degree on the variable of your term, of your terms, and in this case it is 2. So this is a parabola. This parabola here has looks like a y-intercept. If you take a look, that y-intercept is at -10. Now I want you to look at the equation on the left. How does that relate to the equation? Well, you're going to see that constant value at the end of the equation, -10, actually is the same thing. So the y-intercept in any polynomial will always be whatever that constant value is. In this case, it'd be -10. Another thing to consider here I want to talk about is the end behavior. So as this thing moves to positive infinity, as x moves to positive infinity, you can see the y values are getting infinitely bigger. Let's just zoom out and show you that again. So as you get x going from positive infinity to positive infinity, the y values are going up, 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 up. On the other side, as x approaches negative infinity, same thing, the y values are going up, up, up. That is a characteristic of an even degree polynomial, that the end behaviors as you approach x to negative infinity or x to positive infinity, your y values will go either both to positive infinity or both to negative infinity. In this case, they're both going to a y is approaching positive infinity. That's because the leading coefficient of this thing is positive. When I say the leading coefficient, that means the number on the term with the highest degree. So in this case, it's just 1. Okay, so what if we changed that leading coefficient to negative? So if you take a look here, I'm just going to turn off the other graph. So again, this is a quadratic, an even degree polynomial. But in this case, look at the y-intercept. It's +10, the equation that adds up. The end behavior of this particular graph here. Well, as x approaches negative infinity, you can see our numbers of y are approaching negative infinity. They're going down, down, down to infinity. And as x approaches positive infinity, you can see that our y values here are getting, I guess, smaller. So these two functions, familiar, but we would define these as an even degree polynomial, and the even degree polynomial has some tendencies, especially when it comes to end behavior. They end in the same direction, okay? Now, if we're talking about domain and range of these things, now the domain of these things, hopefully you guys can remember, it goes from negative infinity to positive infinity. But the range is a little bit different. Both of these have either a maximum or a minimum value. So the range is going to be dependent on whatever those are. So in the case of this graph, we would go from negative infinity all the way to whatever that y value is, 10.25. And then in this particular case, we would say our range goes from negative 10.25 to positive infinity. So for even degrees, our range is going to be have some conditions on it. So let's investigate another polynomial here. Let's look at the cubic polynomial. These are all going to have varying shapes. They're all not going to look like what I'm showing you here. But this particular polynomial is what we call a cubic polynomial. Now, I'm just going to zoom in a smidge. Look at that y-intercept. It's at 2. Well, if you look at the equation, the constant's also 2, so those add up. Now, look at the end behavior here. This is what we call an odd degree polynomial because the highest degree of all the terms is 3. And 3 is an odd number. So we call this an odd degree polynomial. Odd degree polynomials are slightly different than even degrees because the end behavior is in opposite directions. So if I take a look as I go, x approaching positive infinity, my y values are increasing or approaching positive infinity. And they're getting bigger and bigger as my x gets bigger. And then the other way, as my x gets smaller or approaches negative infinity, my y values are getting smaller or approaching negative infinity. So the end behaviors are in opposite directions, and that is a particular consistent thing with odd polynomials, odd degree polynomials. Also take a look here. We have 3 x-intercepts. So with a third degree polynomial, you can have up to 3 x-intercepts on this thing. Like the quadratic, you could have 2. If I flip back to the quadratic, there is a way you could have 2. There's no way for the quadratic to have 3. There's no possible way. But the cubic can have 3. It can also have 2, and it can also have 1. But there's actually no way for the cubic to have 0 x-intercepts. Because the end behavior is in opposite directions, this thing eventually has to cross the x-axis. So it can have between 1 and 3 x-intercepts. One thing I like to do with graphs to maybe predict what the degree of a graph is take a look at how many times this thing changes direction. We also call this turning points. But if I was to just trace the graph, so I'm going to go, let's count direction changes. So here's my first direction. It goes 1, 2, 3. So I kind of rode that wave 3 different times. Because I did that is an indication that this is a cubic polynomial. So 3 kind of direction changes. Let's take a look at the negative leading coefficient odd degree polynomial. So this is our cubic polynomial again. This time we flipped the leading coefficient to be negative. I want you to think about that in terms of like transformations. We just multiplied this thing essentially by negative 1. All of our y values essentially flipped. This thing was reflected across the x-axis. So if I took my original graph here and I reflected it across the x-axis, i.e. make the leading coefficient negative, it should look like that. You can see the 2. So that's all I did, was I reflected to give me this guy. So this guy is the cubic polynomial, odd degree polynomial, but with a negative leading coefficient. So it's going to have end behavior in the opposite direction. So the end behavior is going to say, as x approaches negative infinity, my y's approach positive infinity, and as x approaches positive infinity, my y's are getting smaller or approaching negative infinity. And again, the constants here, my y-intercept is -2, and if you look at the equation, the constant's -2. Domain and range here, well, you can see the domain, this thing there's no limitations on my input values or my x values, or if you look at the graph, there's no x values that this graph will not consume. This thing will go from negative infinity to positive infinity in both domain and actual range as well. So there are no limitations on domain and range, and that is consistent with odd degree polynomials. All right, we're going to look at the second type of even degree polynomial. So that's going to be the fourth degree. So let's take a look at the fourth degree polynomial. So it looks like this. So the fourth degree polynomial, pretty close to the parabola. It just has an extra little hump in it, I guess. But if you look at the end behavior is in the same direction. They're both going to, y is going to positive infinity, both as x approaches positive infinity and negative infinity. Same direction here. The constant value and the y-intercept are the same. The domain here, there's no x values that this graph doesn't consume. So this thing would be from negative infinity to positive infinity, all real numbers in the domain. Now the range, however, because this thing ends in the same direction, when we're talking about end behavior, there is going to be a bottoming out point. So the range is going to have some limitations on it. Okay, and look at the x-intercepts. A fourth degree polynomial can have up to 4 x-intercepts. Now, a fourth degree or even degree polynomial for that matter can also have 0 x-intercepts. It could be, this whole graph could be above the x-axis or reflected and all below the x-axis. So there is a possibility for a fourth degree to have, or an even degree to have no x-intercepts. Let's take a look at with the negative leading coefficient. So if I have a fourth degree with a negative leading coefficient, it essentially just reflects across that x-axis. And it's going to have the other end behavior. The y values are going to approach negative infinity as we go either x to positive infinity or negative infinity. Domain is going to be the same. Y-intercept and the constant are consistent. In this case, the range will have a max value. So the range will have a condition on it. In this particular case, it'll go from negative infinity to 8.88, or let's just say 8.9 in this case. So we've looked at odd, even degree polynomials. We're going to look at our last odd degree polynomial here. Our last odd degree polynomial will be the fifth degree, which looks like this. Now again, a fifth degree polynomial, it kind of looks like the cubic. It has this opposite end behavior. One end goes to y is approaching negative infinity, the other goes to y is positive infinity. But I want you to look here. Let's ride that wave again. Just count the turning points. Not the turning points, just count the changes of direction, okay? So let's say we're going up, we're going 1. Oh, sorry, let's just keep that on here. Give me a sec. Let me just get my finger on the graph. So it's 1, 2, 3, 4, 5. Hope you guys saw that. I'll do that again if you wanted. So 1, 2, 3, 4, 5. So it's not always going to work out that nice and smooth, but that's an indication that we're dealing with a fifth degree polynomial with those 5 kind of, changes in direction. So with this guy, you can see, look at the y-intercept. Y-intercept 0. This particular guy doesn't have a constant value, so that should add up. There's a 0 constant value, so therefore we have a y-intercept of 0. And we talked about the end behavior. It is in opposite directions. So this has a positive leading coefficient. And yeah, this would be our odd degree polynomial. Let's take a look at the next case. This would be a fifth degree with a negative leading coefficient. Again, this one's just a reflection of the other graph. But look at the end behavior. The end behavior goes in opposite directions. Yeah, you look at the domain and range. The domain and range, well, the domain, all the x values, this graph does consume all those x values. So it is from negative infinity to positive infinity in terms of domain. Range as well. There is no max min value. There's like these little, we call them local max and mins, but we're not going to worry about that. there's no actual absolute max or min here. So the range here is all real numbers as well. So that's kind of a little dive into the characteristics of polynomial functions and some of the basic characteristics that we're going to look at. For now, that's all I got. Thanks.